Geologic rock formations, or what I also subtitle as field trip geology. You know the rocks now, but there's a little more to rocks that we haven't discussed yet, and so I would like to do this now. Once the sun is coming back out and you can crawl around the mountains again and get out and fresh air everywhere, you then will see something a little bit different, and we're going to discuss it. Geologic rock formations. So what is a geologic rock formation? It's not just a rock sticking out of the ground. It is a term. There's a whole science behind these rock formations. It is something that you will learn in geology a lot of, and especially when you go out in the field, you need to start becoming familiar with the rock formations you see and how to identify them. So what is actually a rock formation? And a rock formation is a large layer. Think about it as a sheet of a rock, of a specific and a particular and distinguishable lithology or rock type. Think about a sheet of sandstone. Now, when I talk about a sheet of sandstone, I don't mean, just a few inches thick. I'm thinking about hundreds, thousands of feet thick that covers a large area. How large an area? Well, in some cases, several states. Huge layers. Now, is this layer continuous and all the way solid through? No, because erosion has poked holes in it and we cracked the rock and we moved it up. So it is a little bit shook up, and sometimes we have erosion that cuts holes through the whole layer. It looks like a piece of Swiss cheese, right? That you peel off, and it's a layer, but it has holes in it. So it's a Swiss cheese of a rock layer that is laid down. But it's distinguishable. You can see, it has a color, a texture. It is made out of a specific rock type, of a material, and I can follow it over large distances, right? Now, those things are laid down laterally over incredibly large areas, as I pointed out, hundreds of square kilometers, but they have holes in it, like Swiss cheese, right? And they also have a certain age. They were deposited at a certain age and often at a certain geographic location, which we call depositional environment. Here we're meeting all kinds of old friends that we discussed in our sedimentary rock system. So there is a certain age. Certain sandstones were laid down during the Jurassic or the Triassic or the Devonian, and you will kind of get familiar with this age. So we often can assign an age to these monstrous rock layers that are laying down, right? And they are associated with certain what we call a certain paleogeography. As you know, if you take geography, especially physical geography, as a course, you know that we divide the earth, the surface and the earth, into areas, highlands, flatlands, coastal areas, and so forth. We can do the same with these things that happened long time ago. We call this a paleogeography. For us, these are depositional environments. Aeolian, lacustrine, marine, deltaic, shoreline, you know them. Alluvial fans, they also coincide with my paleogeography. Now, a rock formation can be any rock type. It can be sedimentary, it can be igneous, it can be metamorphic. However, even so, it can be any of those. The bulk of this rock formation studies, of investigation of rock formation, is going to be sedimentary. We're going to stick for most part in the sedimentary realm. There are some metamorphic rock formations. We're going to mention one, but the bulk is really going to be sedimentary, because sedimentary are our storytellers. They tell us a lot about what the earth was like in the distant past, and we can distinguish, we can figure out what happened, we can figure out what happened to the climate, we can figure out if the sea levels were going up and down, and rock formations tell us all of that. Now, sometimes there are layers in a formation that are way smaller, kind of maybe just a few tens of feet or just a few inches thick. Now, these layers may be significant. They're not kind of, oh, if it's this small, do we bother? Well, they can be very, very significant. We call these smaller units beds or members that are smaller, even if they are only a few inches thick. I give you one example, one that's pretty famous in southern Colorado, if you want to find it, and this is the so-called KT boundary. The boundary between the Cretaceous, the end of the Mesozoic, and the Tertiary. This is when the dinosaurs were wiped out, right? Now, we now know that this timeline coincided with a humongous impactor from out of space that hit somewhere in the Yucatan Peninsula and caused a global catastrophe that wiped out all life within a few days, at least surface life, unless you were burrowing underground. So we have some evidence of a very, very global catastrophe. And there was, of course, material thrown up into the air as this big impactor hit and settled all around the globe. And we have this very thin but very distinct layer that we can find as far away as Italy, and we can even find it in Colorado and Trinidad, and this is a KT boundary layer. It's about 1 inch, 2 inches, in some places 3 inches thick, and it is a residue from this global impactor that would be a bed or unit, the KT boundary. We call it actually KT boundary layer. Depending if it's a little thicker, we call it a member. If it's a little thinner, we call it a bed, often referred to as the KT boundary layer. That can be found not far from Trinidad, Colorado. It's one of the best places. Geologists from all over the world come to Trinidad, Colorado to see it there. It's, I've taken students there. It's fun. You can actually put your finger on it that, oh, this was the monstrous event that wiped out the dinosaurs. Now, we can also take 2 or more formations and group them together, lump them together. Sometimes it is, it's a very good idea, especially if a lot of formations, and we call this one a group. Well, duh, this is a simple verb, so we call it a group of formation or a group. That is when we lump them together. So this is these rock layers that we have spanning many, many states and places. So, formations, large sheets of rocks of some pretty good thickness that lay down one on top of the other. Here's an illustration, something like this. So you have one layer, then the environment changed, and there's another layer, different type, and there's a blue layer, pink layer, of course, and it stacks up. They stack up like, when you make pancakes, you put one pancake down, the next pancake on top, the next pancake on top. So eventually you have this stack of layers that have been laid down, of course, over an extensive period of time. that expand, how far do these layers go? Well, they can go very far. Let me show you one of these layers. Now, again, think about it more like a Swiss cheese, not one solid layer. As you can see, pokes holes in it, and here's a little remnant of this blue layer sticking out. So, yes, it looks more or less like Swiss cheese. But there's one famous formation, one of those rock layers, that is famous for Colorado, and also for other states, because this is where many dinosaur finds have been made. This was during the time of the dinosaurs. It's a Jurassic rock layer. It's from the Jurassic time period. And this is how big that sheet is. It covers basically all of Colorado, with the exception of a little bit on that southeastern corner here. All of Wyoming, at least 3/4 of Montana, goes all the way up into Canada, North Dakota, South Dakota, even Nebraska, pieces of Arizona, and even half of Utah, and pieces of New Mexico. So this is a huge layer, one of those that you can follow from Colorado all the way into Canada, and you see it here again and there again and poking out, remember Swiss cheese, but it is a huge rock layer. Now, we often don't see this whole extent because it's often buried underground. It's still there, but it moves in the subsurface unless erosion kind of has it poking out on the surface again. And to somehow illustrate that layer, and we know it's a stack of pancakes, we kind of draw it as such. So it's very prolific in Colorado, one of the famous ones. We draw it here as what we call a stratigraphic segment or section, basically just showing the edge of my stack of pancakes. Now, I'm going to put some more other formations in it. The Morrison is not the only formation. Actually, the Morrison is sort of the top. That's in the Jurassic right here, and below it there's some other formations. One is called the Entrada Formation, one is called the Lichens Formation. They are below the Morrison Formation. There would be these layers kind of going along, again, over large distances. I'm just giving you a group. When I made a group, actually, that's a perfect example for a group of the Morrison, Entrada, and Lichens Formation all stacked together, with the Lichens being on the bottom and the Morrison on top of that stack. I'll show you another layer. It came way later, came in the Cretaceous. It is very large and goes over a large area. Here we go. This is the so-called Pierre Formation, or the Pierre Shale. And this is its extent. So I overlaid that pancake right here, arched-looking pancake. But this goes way into Canada. I mean, you can follow it all the way up into Canada. But it also is on top, somewhere on top of the Morrison, because as it overlays Wyoming, it also overlays all of Colorado. Again, Swiss cheese. Think about the Swiss cheese thing. And some other states. Where would this be on my stack of pancakes? Well, this is one of my upper pancakes. It's right here. We're missing some pancakes, as you can see that one. What I'm creating here, looking at my stack of pancakes sideways, is what is usually referred to as a stratigraphic section. I'm drawing a stratigraphic section with all these stack of pancakes as they appear in sequence, right? Now, I need to fill in the blanks. As I said, I give you just 2 examples. There are many more, and I would need to draw many more pancakes. And as they extend, it would be kind of a mess right here to doing the map view. But on the stack of pancakes, for example, we have some other layers. There is a Dakota group here. There's a Benton Shale, Niobrara. Then comes a Pierre Shale. That's the gray stuff in there. And then here's my Morrison and the Entrada and the Lichens down here. There's my other group that is stacked up here. So I'm getting this stack of pancakes, side view, basically, of all these rock layers, Swiss cheese style, that are stacked on top of each other. And this one is specific for the area for the northern Colorado Front Range, Fort Collins and Loveland. This is what you will find there. In different places, there is an additional pancake, or we remove some pancakes. These pancakes are no there. They are gone by erosion or something like that. So, but this pancake stack here is specific for the Fort Collins Loveland area. You would see all these layers in sequence. Now, we can add a few more for the Fort Collins Loveland area. What is below my Morrison? There's in the Lichens Formation, there's something called the Lions Sandstone, and there's a Santanka Formation, which is basically siltstone. And then comes a fountain in the Ingleside Formations. And the Fountain Formation, of course, makes the flatirons and boulders. There's a very resilient conglomerate, or an arkose, that sticks out there. That's Pennsylvanian in age. And then there is kind of below that is a metamorphic layer, very thick Precambrian, we call it Precambrian rocks. It's called the Idaho Springs Formation. That is biotite gneiss and quartzites and amphibolites and schists and all this jazz kind of lumped together. So that is sort of the stack of my pancakes. We call this stratigraphy, that we will find in this area. Now, there are some laws of stratigraphy that I would like you to introduce you to. We're not going to go through all of them, but at least we're going to get started. We'll finish them up later when we talk about geologic time. But there was a man by the name of Nicholas Steno. He lived in the 17th century, and he was a Danish scientist born in Copenhagen, and really called a pioneer in two fields at that time. If you go back to the 17th century, there was not one subject geology, or one subject biology, or one subject environmental science. They didn't have that. So they lumped all these sciences more or less together in what we would now call natural science. And so this is why often famous scientists from the 17th or 18th century, or sometimes even from the 16th century, had multiple degrees. So Nicholas Steno was famous for his contributions to anatomy. I dissected people, and also for geology. They don't seem to be really related, but hey, it was science at this time. It was natural science. So they did the whole 9 yards, if you get my drift. Interesting enough, he later left his infatuation with science completely. He had a career change later in life completely. He actually was dissatisfied for some of these personal answers he couldn't find. And in later life, he switched from science to actually religion, to divinity studies, and became a Catholic bishop, Catholic priest in later years, and spent his time pursuing that career. But he started really as a Danish scientist and gave a lot of really good contribution. In his doctoral dissertation, that he wrote in 1669, he, and this is actually a picture of the cover of his doctoral dissertation, he defined the 4 principles of stratigraphy that are still used today. He was a pretty bright person. He came up with these 4 observations that are universally applicable. We call these, and of course in his dissertation he called it the 4 defining principles of stratigraphy. We now call it the laws of stratigraphy, and they attribute it to Nicholas Steno. I'll go way back, several hundred years back. I know some of you in the course probably have some history background, a little tidbit that might come in handy that, oh, kind of cool. So how was science made or contributed to during that time period? So let's look at his laws of stratigraphy. And this first law he came up was the law of original horizontality. So what did he observe? He observed when unconsolidated sediment is settled down, it's always horizontal. He looked at many diggings into grounds, into fields, unconsolidated sediment, marine sediment, lake sediment, even sand sediment is laid down in more or less horizontal sheets. And so he basically described the first thing, okay, when that then solidifies, the rock layers must also be horizontal. So what did he came up with? He basically postulated that rock layers are always deposited in a more or less flat layering first. Layer after layer, they are all flat. Now, if they are anyway tilted or shaped oddly, that tilting would come later after they had turned into solid rock. So after lithification, after they've compacted and compressed, if then they would be tilted, that would come later in the sequence. But at first he found out, so things are laid down flat, and that's true worldwide. If we would go on a course field trip together right now, which we can't, it's looking good. It's looking like we're starting to opening up things again. I would show you a perfect example of unconsolidated sediment that eventually will turn into conglomerate if we wait for a few million years. But it is laid down flat, makes actually a flat surface. And we can see that. I'm going to show you some slides here, some pictures where you still see if things have not been deformed and there were no earth upheaval processes. My rock layers are more or less horizontal going through. Here's another one, a nice canyon dug, and you can see the horizontal layering right there, horizontal layering, as it is laid down completely flat. And many rock layers, if you drove even to the Grand Canyon, it's flat, the horizontal layers. You will see that law of original horizontality in action. Here's another one. Flat layers everywhere. Now, are all layers on Earth flat? Of course not. You're going to see some tilts, but keep your eyes open. In many places they are flat, except the Front Range of Colorado, where they seem to be tilted. Well, we'll get to that in a second. But if you go like to the Grand Canyon or Kansas and you see some rock layers, they're usually flat. Now, Colorado, things are tilted indeed, but this tilting comes later, comes after the rock is solidified or turned into solid rock. So that tilting came way later, sometimes millions of years later. Now, Nicholas Sterner also defined another law. We're going to give you law number 2, and I'm probably doing only 2 laws right now. We're going to add the rest later in another module. But I'll give you a second law. It's very important. This is called the law of superposition. Another stratigraphic law. The law of superposition. What is that? Well, the law of superposition basically states that rock layers are laid down first are the oldest. The stack of pancakes on the bottom of the pancake stack was served first. Anything above this becomes subsequently younger. Any other pancake I put on top of it is served later and later and later in a linear time continuum. In other words, the oldest stuff is on the bottom. The youngest stuff is on top. This is universally true for all rock layers. It's true for pancakes. The oldest pancakes is on the bottom of your stack. The youngest, the freshest one is on the top, unless you flip the whole thing around, of course, and you cheat. But if you leave it alone, this is what you find. It is also true for other systems, crime scene investigation. We can stack all kinds of things up. For example, tracks in the field of snow, right? Who crossed the snowfield first? Well, it's the track that is on the bottom and it's crossed by all other tracks. So in this case, it is these tire marks. They are crossed over by other tracks and walked on by other tracks. So these are most likely the first to appear and are the oldest. So oldest stuff is on the bottom, youngest stuff is on the top, and you could now decipher these tracks as well. You know, who walked over the field last. A fun little activity. I'll let you figure this out. Sometimes it's easy to see something. I'm not quite sure. Is it the blue one? Or is it the orange footprints here that were the ones that were the latest? Well, sometimes it's very easy to decipher. Sometimes it takes a little deductive reasoning. I'll show you another picture. I love this picture. It's a picture from Hawaii, and you can see a lava flow, right? Here's a beautiful lava flow. You also see it's laid down more or less horizontal, and it is on top of the road. Now you can ask the question, which came first, the road or the lava flow? And of course you will immediately say, well, the road, of course, because the lava flow kind of bulldozed over it. So the lava flow must be younger than the road. Road's on the bottom, lava flow is younger, it's on top of it. And I sometimes joke, no, it's the road's older. They built it right, it stopped right here with the road. Of course, it's nonsensical. They wouldn't do things like that. So even in fairly young events, you can see the law of superposition. Oldest on the bottom, youngest on the top in that sequence. So, oldest, youngest, law of superposition points toward that a little bit. Let's take a look at the rock outcrop. This one is a picture I took at the Colorado National Monument in Grand Junction. And you see some beautiful rock outcrops, and you can tell which are the oldest rocks and which are the youngest rocks. And you can see they're fairly flat right there. Of course, the oldest one must be in the valley there, in the bottom. That is my oldest rock. It's visible to me. Are there older rock? Yeah, if there's anything buried below that, of course it must be older. But from what I can see, if I look over this beautiful landscape, I can tell you that the oldest rock must be in the bottom of this valley. And the youngest material must cap that rock right there. It's on top. It's the rim right there. That's the younger one. If I find some more on top of this cap, well, of course, that would be younger than that. It looks like over here, this is something that's even younger. But for the spire here, that is the youngest rock I can see right now. That's on the top. Law of superposition. Okay. So let's leave these two laws be for a little while and walk forward and look at our formations again. How do we identify formations? Well, formations are given names. And these names and that is a common practice. That's the practice that we have adopted, is we give names to a formation, that refers to a geographic area where this formation was first described or is most prolific or is, that's what we call the type locality. If you want to know what that formation looks like in all its beauty, then you go to that geographic area the formation is named after, and that is exposed in its essence, best example form. Of course, it can change as we travel around, as landscapes change when we travel nowadays, but this is the formation name that is given. And we also often draw formations in a stylized form, my stack of pancakes, in a stylized form with symbols depicting what lithology makes up that formation and how easily the formation weathers. And this is often what goes into my drawing. You know, a picture is worth 1,000 words. If I can give it a symbol, then I don't have to explain much. People can see, oh, this is a sandstone and it weathers easily, or it is very resistant to weathering. Let me show you how this is done. I'm going to give you a picture here, and this is a picture that shows 3 formations in sequence. So here is a formation right there called the Moenkopi formation. It's on the bottom. They're all horizontal. Oh yeah. Which law is that one again? Law of original horizontality. So they're still horizontal as they were laid down. The oldest one is on the bottom. Youngest one is on the top. And you can see the bottom one is what we call the Moenkopi formation, has a certain color, certain texture. Then I have a variegated formation in the middle, comes with all kinds of colors and various layers, called the Chinle formation. And then the top is a thick, resilient cliff-forming layer called the Wingate sandstone. And that one is Triassic in age. Kind of makes this layers. And it doesn't take too much imagination to see where we find the break in this formation, though the boundary between the Moenkopi and the Chinle is where we change lithology right here. Here we have a cliff former, kind of a sloping material, and then it gets more resilient right there. And then we have another slope former, which is usually shales or something. Shales like to form slopes, but it's a different color. You can see it until we hit that cliff up here, the very prominent cliff of the Wingate sandstone that is very resilient to weathering. Now, this is what I observe in the field when I go out. 3 formations stacked on top of each other. How would I draw that? Is there any way I can do this? Yes, I can draw this in kind of a stylized, so the Wingate is a layered sandstone. The sand is usually stylized by dots, and you can see I'm coming out to the left quite a bit, which means it's resilient. It's resilient to erosion. So it's a cliff former. Wingate sandstone. My Chinle formation is made up of 3 members, the Owl Rock member, the Petrified Forest member, and the Shinneram conglomerate member. The conglomerate is kind of this funky material. It's supposed to be conglomerate. You draw it like you see it. The other ones are softer. This little dash dot system is softer, kind of slope forming material. By the way, the Petrified Forest member in the Chinle formation is called because this is where the petrified trees are located. If you go to Arizona, to the Petrified Forest National Park with these hundreds of petrified logs of lengths of 50 to 60 foot. It's really a sight to see. They are found in the Chinle formation and more precisely in the Petrified Forest member of the Chinle formation. And they will tell you this in the park when you drive through. So, you can see already by my indentation here, I'm moving further to the right, that this part of the Chinle Formation, or the Chinle Formation itself, weathers more readily. With the middle part, you can see this one right here, with the middle part of kind of sticking out more, a little bit more resilient to weathering, more of a cliff former right there, stylized in my graphic right here. We can then go to the Moenkopi Formation. You can see that one. There's a cliff right there and a slope forming material right there. Well, this funky symbol, it looks like a brick, is actually the symbol for limestone. Oh, this is a limestone cliff right there, resilient to erosion. And then we have the siltstone or shale. These dashes are shale. Dots are little fine dots with the dashes are siltstone. That is way softer. And you can see I'm drawing it toward the right again, showing you that I have something that weathers more easily. So by looking not at the picture, but at a stratigraphic section or column, I can tell a little bit about the rock type. That's what I use for my dots. Color here, why they draw it green, I do not know. It's irrelevant. The colors often that they add to it has to do something with the age. Jurassic materials are often changing to blue, and I think Triassic materials are greenish. Not that it has to be that way, but it's often colored that way to give you somewhat of an age visual, in other words. But this is how you would draw it. And then, of course, you can draw the thickness to scale. I know that the Wingate sandstone is fairly thick. Chinle is a little bit thinner. And then the Moenkopi, those two members, the limestone member and the silt shale member have also different thicknesses. You can see that. So that would be in your notebook as you take notes, for example. Instead of writing it all down, you can draw it like that. And then you can come back and remember, oh yeah, now I remember cliff former, slope former, mostly slope formers, cliff formers here again, because of how far out my little noses go on that one. Now, can we recognize formations? Yes, and that is one of the things we teach you in our field classes. How to identify a formation. Why is it important? Because you then can orient yourself on where you are in my stack of pancakes, and then you can start telling a little bit about what happened during that time. What was the depositional environment like? What was the climate like? What animals were running around? Did we have forests? Was it a desert? So once you recognize formations, you can do all of that. So let's give you a look. Here is a picture. And you can definitely see that something is going on in the picture, that this stuff on the bottom doesn't look like the stuff on the top. First of all, the color is different, but you can also see that the texture is different. That one on the bottom looks like pancakes with syrup dripping down the side. I mean, just making that up. Need something comparison. And there's a little bit of a slope former, and this looks like something more solid cap. So without even knowing what I have, I can already say there are some differences. I'm drawing a line there, some differences between the bottom stuff and the stuff on top. I can definitely see a change here. Some changes going on. And if I drew this one stylized, I can see, well, the bottom one here is definitely a cliff former, right? If I then investigate and say it's sandstone, I can make them all for little dots. Maybe hard to see on the screen, but there's a little tiny dots all over the place. So I would indicate sandstone. This one looks like slope forming erosional material with layers in the middle. They're a little bit resilient. If when I investigate, here I use lines for my shale, the brick pattern for my limestone, little limestone members or layers that are sticking out right here. And the top is a little bit more resilient again. And when I investigate, I may find out this is a sandstone, not quite as good as a sandstone as the one on the bottom. So I can make myself a mental, or better yet, a written note, a written drawing in my notebook, take a look at it, take some notes down about the color and what the stuff is made out of, and then I can hop in my car and drive maybe 20, 30 miles and see what I can find there. So in a little bit of a distance, I find stuff, and that material in the middle looks very much like the one I have found there. I look at my notebook and I come to the conclusion, oh, this kind of stuff on the top here looks very much like that. That middle part looks very much like that, and the bottom part with my pancake stacks, you can't really see it. The resolution is not good enough, but I'll find on the bottom again. So, oh, look, 30 miles away, I find the same stuff. My formation layers going over hundreds of square miles, every now and then with a hole in it. Remember my Swiss cheese analogy, right? But they're basically layers that I can follow in the car. But something is missing right here. I find these layers right there. Here it stops. But on this, 30 miles away, I find another layer on top of this layer. Well, where does this go? Why is it missing here? Our enemy, erosion. Erosion pokes these holes in my Swiss cheese. And in some places they are missing. Erosion did it. Now, as a geologist or somebody who wants to become familiar with the matter, with the subject matter, you always ask which pancakes are below my feet when you walk on the surface. So do I have stacks of pancakes below my feet, layers of formation below my feet? And which are up in the air? What I mean by up in the air, which ones have eroded? So I look. Geologists are not only interested what is below their feet, they are all also interested what was there in the sky once that is no longer there. And by traveling around and taking field trips, I can start making these connections. This is why geology is a field trip heavy science. We want to decipher the history of the earth. I want to know what layers were there once in this place that are no longer there. Thankfully, I can travel and I can see, oh, this stuff was there that is already eroded in this place. And so I'm piecing things together. But I need to travel. So stratigraphy and the deciphering of things are related with field science, which what I can observe. So stratigraphy, the definition of the stratigraphy is the geometrical relationships between formations. The relationships between my pancakes in the stack. How do I define this? Well, I can have a vertical relationship. How does my pancake stack shift from one pancake to the next? We call this a relation or change with formations above or below. Has my depositional environment changed? Was there a volcano? Did mountains rise up? Did sea levels rise? And did I get all of a sudden an inundation of the oceans over the same geographic area? So this is my vertical relation. I can also have a horizontal relation or change of the same formation, the same pancake, over a larger distance. What do I mean by that? Well, think about a pancake that is unevenly cooked. One edge is cooked, the other one edge is still gooey. I will see that if I travel along my formation horizontally. What do I mean by that? My formations are not pancakes. Well, am I at one edge of the pancake closer to a mountain and the other edge of the pancake closer to an ocean? I will see that as I travel along these formations. Now let's kind of do a little bit of traveling. And I know this is dry. I wish I could take you all and we could go and actually look at it and look at the rocks and make inferences this way. But the first place we visit is the Grand Canyon. And instead of showing you a picture of the Grand Canyon, I went, when we visit the Grand Canyon, I go and look at the geologic brochures. Do you know that all national parks actually have or should have a brochure that shows my stack of pancakes in that area or my stratigraphic column? So instead of showing you the picture of the Grand Canyon, I show you the stratigraphic column that you can get from the National Parks Office as it's published there. And there you have your stratigraphic column. Included is the resilience to weathering and your symbolism of what rock types you have. Sometimes the name gives it away. The Kaibab limestone. Here's my brick pattern, is a limestone. Here is my hermit shale, and there's my little symbols for shale. Then you can see it on what is going on. And of course, in my little stack, oldest is on the bottom, youngest is on the top. You can see all of this one, and you can see all these formations. And these formations, we go back in the Precambrian, before we had prolific life. Of course, in the upper Precambrian, we started having a lot of life. Looks like these layers are tilted. We get to tilting of layers a little later. But here's my bright angel shale. Here's a shale again. It's on the bottom there. And this age is Cambrian, so we have some Cambrian, Devonian, Mississippian, Pennsylvanian rocks. By the way, all these rocks right here were before the dinosaurs ever roamed the earth. That's very old stuff. Up here, where it starts to be green, that green-colored stuff, this is the time of the dinosaurs. So my dinosaurs kind of starting to pop up and walking around the earth. So very old material. All these rock layers in the sequence gives you some idea, and also the thickness and the resilience of these rock layers gives you some idea when you hike the Grand Canyon. Now, this is what I find in the Grand Canyon. The river made it possible. It exposed all these rock layers as it cut down into the ground. Otherwise, I would have to drill or dig to find that stuff. But hey, the river was my friend here, the Colorado River, and gave me a really, really good insight of what is below my feet. Remember, I always want to know what's below my feet, and there I can see it. If I walk away from the Grand Canyon and basically walk on the surface, you see the top here is a Chinle Formation on top of the Moenkopi Formation. I can now surmise that what is below my feet, miles and miles below, are these layers of rock, not exposed yet. You would need a drill to find them. Now, let's hop in the car and drive north, sorry. We drive north a few 100 miles, 200 miles, and we come to a totally different place called Zions National Park. Again, I walk to the park office and want to get a my publication was a stack of pancakes, my stratigraphic section. All right. Here we go. And this is what they give you at Zions National Park. Oh my word. All kinds of formations. Here they have subdivided it into members. Here are my members, but here's the formations. We're going to take a look at it, and there's a big honking formation right there, very resilient to weathering, called the Navajo Sandstone Formation. It's Jurassic in age. That's the biggest thing that makes all these beautiful features in Zion National Park. It's the big outcrops of these cliffs, of the Navajo Sandstone cliffs that you see there. But let's kind of take a look at the bottom. I see the Kaibab limestone right there. I've heard Kaibab before somewhere. Oh, Grand Canyon. Look at that. Kaibab limestone. Is that truly the Kaibab limestone or just a look-alike, a limestone that looks like the Kaibab limestone? How do I know? Well, if this is truly the Kaibab limestone, the formations on top and the formations below should match. So, Kaibab limestone here. Below it is a Toroweap sandstone. Kaibab limestone there. Toroweap formation. Whoa, that's a good hit. Above the Kaibab limestone is the Moenkopi formation. Look at that. Grand Canyon Moenkopi formation. On top of the Moenkopi is the Chinle. Look at this. A sliver of Chinle right on top of that. So yes, what is missing at the Grand Canyon, that stuff from the Chinle on upward has all been eroded, is still preserved in Zion's National Park. So when I travel from the Grand Canyon to Zion's National Park, I find all the rocks that have been eroded at the top of the Grand Canyon. Whoa! So this is my connection here. So Zion shows me what the Grand Canyon does no longer have. It's gone there. But Zion still has it. Of course, the lowest thing that's visible in Zion is going to be the Toroweap sandstone. Are there any other formations below the Toroweap sandstone at Zion's? Yes, but I would need to drill. They are not exposed. My Swiss cheese hole doesn't go deep enough. It just shows me that part on the edge of the hole. So, but if I took my drill and drilled down, I would find all this other stuff, could drill into the red wall limestone and so forth. Okay, let's do something more. Let's jump in the car again and go a little bit further north. And we'll end up in another place, looks like that, called Bryce Canyon National Park. Again, I go to the National Park office and I said, hey, where's my stack of pancakes? Of course, they're going to look at me funny and they said, hey, my stratigraphic sections, please. Oh, okay. So they give me another publication. I got this one from Bryce Canyon and here it is. And you're going to see even more layers. Because, why do I want this? Because at Zion's, we end up in the Cretaceous period. By the way, Jurassic, Triassic, Cretaceous, we call the Mesozoic. That's the time of the dinosaurs. So, when my Navajo sandstone was deposited, dinosaurs were roaming the earth. But I want to see, the end was a Dakota formation here. I want to see what's above. So let's take a look at Bryce Canyon. What's exposed at Bryce Canyon? There, one on the bottom is called the Dakota Sandstone. Dakota Formation. Okay, I gotta have a little problem. That is the youngest one at Zion's. They don't show anything above the Dakota Formation. Whatever was about the Dakota, by the way, the Dakota is Cretaceous, whatever was above the Dakota has been eroded. So it's no longer there. When I go to Bryce Canyon, further north, I find the bottom layer being something that looks like the Dakota Formation, but I only see the top part of it. I cannot, because it's buried in the earth, whatever is lower than that. So how do I know that this is really the same Dakota Formation that we see over there? The same lithologic material. Well, unfortunately, I cannot figure this out without some help. Luckily, there's some oil and gas exploration close to Bryce Canyon, not in the national park itself, but outside of the national park. And when they drill down, they have to write down on their little driller's sheet which formations they are drilling through. And lo and behold, if you go to Bryce Canyon and look at oil drilling records, you will find Windsor, the Carmel Formation, the Temple Cap Formation, even the Navajo sandstone, still buried deep in the ground, not exposed. So we know that this Dakota sandstone is the same as that Dakota we find at Zions. So there's my connection. Of course, whatever has been eroded here in Zions National Park is still present at the Bryce Canyon National Park. And here we have the Cretaceous and the Tertiary and all the way top to the Quaternary. Quaternary is our age. Woohoo! We are there of what we have now, the now living up there, and we find all the rest of the rocks that are eroded here in Bryce Canyon. Literally, by traveling from the Grand Canyon through Zions National Park to Bryce National Park, we have seen the whole stratigraphic segment from the beginning of times to now. We've done a complete time travel journey through all of our pancakes. Now, I did something that the park doesn't do. I decided, can I cut these things out and kind of paste them all together to give me a complete picture of the stratigraphy of all the pancakes, even the eroded ones and the ones that are underground. And I've done that, and it worked out okay. Here is my photoshopped complete segment from the Precambrian all the way to the present with all the rock layers. I try to stretch it and squeeze it so they are have the thickness matches with all of those. And you can see the complete stack of time of my pancakes. My stratigraphic, complete stratigraphic column. By the way, guys, I have to tell you this. This you cannot see everywhere. You are lucky enough to live in a place where, if you want to do that, could do the complete time travel through prehistoric time by planning a vacation in the Grand Canyon and Zions Canyon and Bryce Canyon, traveling around. If you want to add one more gem, one more travel gem of fantastic landscape in it, you can go below the Grand Canyon into the Precambrian by adding to this one as your first stop, the Black Canyon of the Gunnison, which is completely, the bottom there, completely into Precambrian metamorphic rocks. That would be the bottom of the Grand Canyon there. And then you have it all. And you go from the Precambrian, the early beginnings of the earth, all the way to today by making that trip. Is that a plan, guys? Let's go. All right. That would be a cool field trip to see it all. Okay. Let's add a little more. Let's see how far we get. Tilting of layers. what we call the brutal forces of nature that happen, but tilting comes after deposition and compaction. And to make it quite clear, I should write down after lithification, after my sediment has turned into rock. Because if you tilt unconsolidated sediment, you're having a landslide. It all comes rushing down on you. So to have a tilting, and this tilt sticks forever, it sticks together, you must turn your material into solid rock. You must make it rock solid. So let's take a look what we find here in Colorado. So you can tilt it just a little bit. Remember, Nicholas Steno said, the law of original horizontality. So when things are deposited, they are flat. They are flat. Now, if they are slightly tilted, like 10-degree tilt, that comes afterwards. So we need to turn them into rock first, all the layers, and then you can start tilting it. And then you can even erode it, after they are tilted, and make some shapes out of it. This is okay. So here's a 10-degree tilt. And here is a little bit more tilt. Well, 45-degree tilt. This is pretty steep, and then erosion takes place. And then you shed some material around from the erosion. And you can even do a 90-degree tilt and make these rock layers all vertical. Oh, my goodness. Well, you may ask me, Dr. K, do you have examples of that? Where can I see stuff like that? Yes. I don't have to travel too far. When you go out on your field trips, remember, I have these self-guided field trips. Have some fun. Don't only collect samples for your stuff, but, look at things. Go, whoa, that looks cool. Looks cool. So, 10 degrees. Red Rocks Park. It's a little more than 10 degrees. Actually, it's almost 30, some 28. So, but it's a fairly gentle dip if you go to Red Rocks Park. And then, just a mile from Red Rocks Park, my dip has steepened. That's kind of cool. So within a mile, we can go from, not a little more than 10. I have to say that one. More in the 20-ish, lower 30s, something like that. If we go just 1 mile to the I-70 road cut, 1 mile north, you'll see something that is approaching more than the 45, a little less than 45, but it gets steeper, and you can definitely see it. So this is part of my I-70 road cut. You can see these tilts very nicely. There's a parking lot, by the way. It's point of geologic interest. You stop there and you hike up and down. You can see that tilt. It's pretty awesome. Do we find a 90-degree tilt? Yeah, we need to go south. If you go south to Colorado Springs, Garden of the Gods. There it's not quite 90. I measured it once. It's like 88 point something. But close to 90, there's where your fins are sticking out and you can see the erosion. The soft stuff goes away. The hard stuff sticks like shark fins into the air. So right here in Colorado at our Front Range, you can see these different tilts and what they look like of the rock layers. But please remember, these tilts came way after the rock was turned rock solid, until it, way after it turned into a rock, a sedimentary rock. Now, you can see it from the air, this tilting. I'll give you a little orientation. This right here, this kind of little thin line you see, that is C470. That's that interstate. And it turns around here and then eventually meets up with I-25 coming out of Denver. And this is these beautiful hogbacks sticking out, and you can see them tilted, like dipping toward Denver. This is the beautiful hogbacks, and here's your Rocky Mountain uplift. Here's your Rocky Mountains right there. So from the air, you can see that tilting. Here it's about And you can actually see the changes. It's a fairly steep, then it's a little less steep here, and then it picks up again right there. That's a fairly steep tilt again as we go further north. And of course, Golden was under the clouds right here. See the community of Golden. So you can see the tilt. And you can see the resilient rock layers, your sandstones and conglomerates, which are often hard and very, very well glued together. And then these valleys here are by something that is way soft, your siltstones and your shales. Again, very resilient, soft material, resilient, soft material. And there's a little bit of resilient right here sticking out of the ground, little layer as well. So you can see that tilt. Now, why do we have a tilt in the Colorado Front Range? Why is our stuff tilted? And you might already have a guess of what caused that rock layers. Remember, law of original horizontality. Those suckers are supposed to be flat. In Kansas they are. Underneath Denver they are. But you come up to the Front Range and those suckers are sticking up into the air. So why do we have a tilt? Well, the answer has to be within the mountains you are seeing. The story of the Rocky Mountains. The story of the Rocky Mountains. Tilting rocks. We had tilting by the Front Range. Everything seems to be tilted toward Denver or toward the east. And why is that? And that is the story of our current Rocky Mountains as you see them. Now, to kind of back up a little bit, I need to give you a preamble here, and we need to borrow again from our lesson that we started the semester with about plate tectonics. So go a little bit back, about 30 million years, 40 million years, even at the just before the dinosaur got extincted, where whole thing starts. United States looked a little bit different. When here's somewhat of a picture. At this time, we did not have California and Nevada yet, and big pieces of Oregon and Washington were also missing. So we had a much, much smaller continent here at the edge. And there was a plate called the Farallon Plate that was kind of slamming into the North American plate. And this is why we got mountains all around here that started to form. But the question is, so how did we get the Rocky Mountains? So let me kind of explain this a little bit of what happens with plate tectonics as somewhat of a review. So what's happened is, under normal subduction, we have an oceanic plate here, an oceanic to continental plate collision. And what happens is that the oceanic plate is subducted below the continental plate. In this case, it's the Farallon oceanic plate and the North American continental plate, right? And right there at the interchange where we kind of have the subduction going on and the buckling, there's a lot of pressure. We talked about this one. So my continental plate starts to buckle quite a bit. It throws up some elevation at this point. Things are rising, and on top of it, we have this melting going on, and volcanoes are also forming. Now, that goes on today. If you go to the West Coast, you know that there is volcanism going on. May I just say Mount St. Helens or Mount Rainier or Crater Lake in Oregon. So there is some volcanism. These are all active volcanoes, by the way. No, Crater Lake is not extinct. People go there and they say, oh, it's a national park. How cool. It's still active. This whole thing is still active, and we had some rumblings, and you know that Mount St. Helens erupted in, when was it, 1980, and caused quite a bit of havoc down in the, in that area. So yes, there are active volcanism going on where this subduction happens. But if you look at Colorado, we are about a good 1,000 miles away from the nearest plate boundary. We shouldn't have any mountains. We should look like Kansas. So something went on to lift up mountains where we are. Okay, what happens? Now, they figured something out. This is kind of amazing. This is called a normal subduction here. But the Farallon plate on the west coast of North America did something weird. We don't know exactly 100% sure why this happened, but a flat slab subduction was created. One of these ideas, a hypothesis, is that this subduction was rather fast, which means instead of moving, the speed of which fingernail or hair grows into each other, we had a much faster, so that Farallon plate didn't have time to really bend down and be shoved down. It took a while, and it kind of slid below the crust, the continental crust, until it was fairly far inland, and then it's bent down. Of course, it shoved up this gooey material of the mantle. It bulldozed the mantle into kind of like a blob right there as it moved flat, scraping underneath the continent. Now, if you kind of stack up some material, you increase buoyancy. What do I mean by this one? Well, if you have one piece of wood and you put it in the water, it floats, right? But what happens if you glue two pieces of wood together? You make the wood stack a little thicker. Of course, it gets heavier, but it also has greater buoyancy. It lifts up more. And so we generate at this area an additional buoyancy or lift up. Kind of this thing is kind of tries to float higher, and it pushes up. Welcome. Now we all of a sudden can fracture the crust up there, and we can lift up a whole region, including our Rocky Mountains. And that happened, if we go back at the end of the Mesozoic, by the time the dinosaurs got extinct, this whole thing happened, and it went kind of on for 30 million years as our Rocky Mountains were starting to rise and lift up. And so we're getting a blob right here that kind of moves upward, where we have this bulldozed mantle. So this is sort of the preamble of the story. And of course, what happens to all the rock layers that used to be flat around here? Well, that's a good question, right? Well, these ones, they go up in the air, and these ones kind of stay down here. But what happens right at the interface where we have this uplift or these faults going on? Well, something like this. You have the uplifted block with all my rock layers up here, but right there where you uplift, you need to curl up these rock layers upward. You can see this here in this diagram a little bit, kind of have a little curlicue on both sides, eastern slope, western slope, something like that. In the middle, you have the Rocky Mountains. Of course, it doesn't stay flat like it's shown in these diagrams. What's happening is that erosion takes place, and we are removing these layers of sedimentary rock, and basically have the deepest rocks that come from way down deep there now exposed, which are our granites and metamorphic rocks that were way below these layers. Now, here's the deal. On some mountaintops, you can still see a little bit of a remnant of some sedimentary rocks that are not quite all eroded yet. They kind of are left over. But for most part, our Rocky Mountains are really our metamorphic or igneous cores that have been uplifted. But right there, where we have the uplift, you can see the curlicue, and we're bending the rocks upward. And if we take a section, if we slice our earth open, right around the boulder area, you can see that. These are our uplifted granitic and metamorphic rocks. They kind of are moving up. And then my sedimentary rocks right there, they have to kind of curl up, and that's what you see here. You have Fountain Formation and the Lions Formation and the Lichens Formation, the Morrison. The whole stack kind of get tilted up. Now, if you go, of course, now toward the east from there, all these tilted rock layers flatten out, and underneath Denver, they are horizontal again. But if you move toward Golden, you're right at this area where they have been bent up by this uplifting block of the Rocky Mountains. And this is why we have this interesting story of our hogbacks right here, where those things kind of stick up vertically. Now, you can see again, right there, Lichens formation is soft, forms a valley, but the Dakota and the other sandstones here, they form ridges. This is our hogback. So whatever is a little bit more resilient forms a hogback, and the softer clay, like the Benton Shale here, makes a nice valley. And then the Pierre Shale is really, really big, makes a valley, Boulder Valley, right behind there in that big blob of Pierre Shale. So this is the story of the Rocky Mountains and why we have these bent hogbacks, these tilting layers right here in our Front Range. Now, you can see it. Here is the famous I-70 road cut. When they built the I-70, they had to slice through these hogbacks. We call this a Dakota hogback. So this is your resilient rock right there. And this is some of the Morrison formation, which is really soft down here. That's my valley former on the other edge. But the law of superposition, as proposed by Nicholas Steno, works on tilted rocks as well. The rocks do not have to be a flat stack. How does this work? Well, if you know which way they are tilted, you can figure it out. So here's our tilt. Rocky Mountains would be right there. Right? So my I-70 corridor. So we're going, this lane here is going westward. This lane here is going eastward. The other side. So my tilt happened like that. That's my tilted rocks. Now, if you know that, where are the youngest rocks? Where are the oldest rocks? Can we figure this one out? Of course we can. All right. So my oldest ones are on the bottom of the tilt, since we're tilting it upward. You can see the stack right here. Oldest ones are right in this area. And the youngest rocks would be then on top of the tilt, right on the other edge. So you can still use the law of superposition even on tilted rocks. Remember, tilting comes way later, after rock has already been compacted and lithified, turned into rock, and then sometimes millions of years later, we can tilt the whole thing upward. And this is exactly what you see here on the I-70 road cut corridor. With the oldest ones kind of in this end, the youngest ones are the ones here on that edge of the hogback. Right? To reiterate, one more time. Tilt comes after the layers are deposited and turned into solid rock. So tilting is always younger than the actual deposition and lithification of my rock layers. Okay, so law of superposition and law of original horizontality is our starting points. As we progress in the semester later on, and the other module, I don't know which module it is, way back at one of our end modules, we're going to revisit these laws again because there's some other things. When we talk about structure, we can talk about that as well. Now, something else can go on. We talked about deposition, and you also know already that there's some erosion going on. So the story of the Earth is not a continual story of deposition and everything is flat and then we tilt it once in a while. Well, there could be some pause in the deposition as well. Let's look at a possible example. So let's say we're starting to lay down some rock layers. There's my ocean, right? So we're laying down here the oldest one on the bottom, again, one rock layer here, then another rock layer. And we have 5 rock layers, 1, 2, 3, 4, 5, that have been deposited over time, right? So that's the picture. And so far, so good. But the sea then may go away, and this whole thing may lithify and become solid. And we have a regression, a C regression, and C moves backward. And all of a sudden what happens is we may now create some buckling, and a mountain will happen here. Now mountains are always the target for erosion. That makes sense. They have a high potential energy, maybe lifting him up, and so gravity wants to take hold of him and pull him back down. And if we start creating our physical weathering up there and our chemical weathering, these mountaintops start to kind of being chewed up. And what will happen is, of course, all solid rocks around, what will happen is that I might create an erosion surface over time that looks something like this. We are basically leveling out the mountain again. And now you can see I have some tilted rock layers, and this is somewhat what we would see nowadays in the Rocky Mountains as you see them now. But it doesn't have to stop here. Let's say that was in a distant past, and what we do next is we're gonna deposit some more rock layers on top of it and make them solid again. Oh, now we had a line here, this little blackish darker line. And what happened there is that this was a time of erosion. There was no deposition going on. There was a mountain there. We're going to take care of the mountain. We kind of leveled everything off. We created literally a break in our time of deposition. A time break, if you want. That's lost. That has been eroded, and then we deposited something on top of this eroded surface again. Now, here are some rock layers on the bottom meet some rock layers on the top on an angle. You can see it very, very nicely here. These ones are tilted down here. These ones on top are not tilted. So the lower layers meet the upper layers at an angle. We call this break, this old erosion surface, this time break, an unconformity. It is unconformed to what has happened, what's supposed to be happened continuously, like building up layer after layer, oldest one on the bottom, youngest one on the top. Somebody stole one of our pancakes out of the pancake, literally. We basically ate the top few layers of pancakes, they're all gone, and then, somebody supplies some more pancakes, we throw this on top. So we have an unconformity, which is a break in time, or a break in the depositional record, and then we put some more on top of it. Since these layers, in this case, meet the top layers at an angle, we call this an angular unconformities. And for students, and even professionals, angular unconformities are super easy to spot. You can see them. You can walk around and you know, on top of this angular unconformity, on this angle right there, there must be a time break. I'll show you some. That's a old friend, the Grand Canyon. And if you stand on the rim and go, ooh and ah, like everybody else, and look over the vast, beautiful carved rocks, and you look way down, look what you see here. I see some rock layers on the bottom. They are a little bit tilted. I have to admit that tilt is not very steep, but it's there. You can see it. But then, look at these rock layers. They are all horizontal in the Grand Canyon until you come down to this point right there, where we've switched from a horizontal and everything below it is on an angle. Welcome. You just discovered an angular unconformity. There is a time break right there. You can actually hike down, put your finger on it and say, yep, this is where erosion happened. For how long did the erosion happen? Who knows? Probably going on for several million years that are missing from our rock stack, and then stuff got deposited on top of this one again. So the rock layers you see in the Grand Canyon are not one humongous event that all placed them there. You can actually see time breaks in there, and an angular unconformity is super, super easy to spot. Here's another one. This one is actually in Scotland. And you can see these rock layers here, what this person sitting on. They're almost vertical. sticking up vertically. But then you look behind this person, and these rock layers, while still tilted, are much more horizontal. They have a much more horizontal orientation. And what does this person do? He puts his fingers right onto this interface between the vertical rock layers and these other rock layers. He again found an angular, we still would call it an angular unconformity. This angle is rather steep where those two rock layers meet. It's a time break. These rock layers were deposited all horizontal, then tilted till they are almost vertical. Then erosion happens, and then we deposit more stuff on top of it, which of course was horizontal before then. So this thing was tilted several times, and created this time break, this unconformity here. So angular unconformities, very easy to spot. Now, sometimes there is a change in rock type. So here's a stratigraphic section. You all should know by now what stratigraphic sections are. And in this stylized stratigraphic section, you see a sandstone and a shale and a limestone. Well, all of those are, of course, sedimentary rocks. But then down there, you see some metamorphic rocks. How come we can put a sedimentary rocks directly on top of a metamorphic rocks? Well, not really, because if there would be all one stack, the sandstone should have metamorphosed into a quartzite. So if you have a change in rock type, that usually indicates, with very few exceptions, but it usually indicates a time break, a time of erosion. And therefore, right at this interface between these two rock types, we have another unconformity. This unconformity is called a non-conformity. A non-conformity, meaning that my rock types are changing. In this case, from a metamorphic to a sedimentary rock. And that usually means we have another time break, another break in time where erosion happened before deposition took over again. So we change our rock types. And by the way, the change could be igneous to sedimentary or the metamorphic to sedimentary. By the way, metamorphic to sedimentary is very common. We have it in Colorado as well. We call it the great unconformity here in Colorado. And when you have time, once the snow melts and you want to go up to Red Rocks Park, upper parking lot, you need to go to the upper parking lot. If you then walk from the upper parking lot toward Denver, you get into the amphitheater, of course, where all the concerts are. But if you go just for 100 yards in the opposite direction to the edge of the road there's actually one of the best examples of a nonconformity, I would say, in the world. And it's right here in Colorado. And they have a bronze plaque that they put there, and it says, the great unconformity, and it's a little arrow. And that's an interface between our metamorphic, what we call the Idaho Springs Formation, metamorphic rocks, and on top sits the stuff that Red Rocks Park is made out of, called the fountain conglomerate, the fountain formation, the fountain arcos sits right on top. And you can see it. You can walk up there, put your finger right on it, here at our Red Rocks Park. So, nonconformity is where we change rock types. Here's another one. It's usually a smaller time break, not a big one. Here's two rock types in this picture. Maybe hard to tell, but there's a brownish gray, dark gray, fairly hard rock on top, and there's some kind of reddish stuff underneath. That on top you see right here is actually a lava flow that has hardened, of course, and below that is some other, looks like sedimentary rocks. Okay, so right here you have a break again, a small time break. These sedimentary rocks was there, and then the lava flow went on top. And so we have a basalt and then maybe sandstone, siltstone below it, and you have another non-conformity, even so that time break is much smaller. We're not talking about millions of years here, because the basalt flow is much thinner and it's more localized event. But still, you can see a change in rock type, sedimentary rock to igneous rock. We still would call this one a unconformity, specifically a non-conformity. My rock types are changing. Now the last one is the most difficult to spot. Here I am took this picture in a little community just north of St. George, kind of 15 minutes north of St. George in Leeds, Utah. And you can see this here, some straight layers down there, and there's some other straight layers on top, but there's this funky line going across right here. What I'm seeing here is another unconformity. It's very difficult to spot. Here it's rather obvious. Yeah, I have different sedimentary rocks that abruptly change, and they're not changing gradationally from one on the top, but actually a little bit of a sloped change here. This particular time break or unconformity is called a disconformity, and a disconformity is the most difficult to spot because sometimes it's right in the middle of a huge stack of rocks that has the same color above and below the disconformity. And the only way to spot that there was a time of erosion going on and not deposition is because my fossils above and below the disconformity change very abruptly. And then when geologists go in and they look at the fossil record above and below this, they go, whoa, wait a minute, we just made a jump of 10 million years. How does this happen? Well, you just discovered a disconformity. By the way, disconformities are the most difficult to spot. This is a fairly obvious one, but most of the time there might be a disconformity right in the middle here, parallel to the rocks, and you would not even notice until you take a very, very close look, and you can see that type of break in the rock record. This is unconformities that happen in nature as we stack up our pancakes. Basically, the case of the missing pancake. All unconformities are break in time. If we stop deposition, we basically stop our clock. There's nothing going on until we stack something back up again on top of that. Okay, what else can we do with rock formations when we interpret them? One thing we can look at is so-called sedimentary facies or sedimentary sequences. What do I mean by this one? Okay. You already know that certain types of sedimentary rocks are associated with certain types of depositional environments. For example, if I would have a spot quiz right now and throw this one out at you saying, well, where would you find conglomerate? You should say alluvial fan, right? That's the most common one. Exactly. Bingo. Or if I say limestone, marine coral reefs, bingo. Or if I say very fine, super well sorted, super rounded sand, stone, sandstone. We're talking about rocks. Okay, now you have to think a little bit about, okay, now sandstone, I could have rivers, I could have beaches. Where else can we find sandstone? Oh yeah, sand dunes, right? How do we distinguish those? Well, if I say very well sorted, very well rounded, that leads me toward the dune, the aeolian environment. So we all know that certain sedimentary rocks are associated with certain depositional environments. We can play this game a little bit. We call these depositional environments if they are time equivalent. Now we're going to show this to you in a second. If they are time equivalent sedimentary facies, which means we can have next to each other different sediments being deposited at the same time. We've seen that with rivers, right? We've played around with rivers for a while, and you know, oh, river can erode and deposit at the same time. That was kind of weird as the river shifts course back and forth, right? But we can also have something that happens at the same time along a certain system. In this case, we talk in the near shore or the marine environment. So close to the coast, you're going to have sand. We talked about this too before. Close to the coast, you have sand. We call this a sandstone facies. But at the same time, as the sandstone is being deposited here a little bit further out to sea, where the water is quieter, we settle down the very fine material, and we get these shale or mud facies, right? And if you go a little bit further out, actually you starting now quiet water that starts to clearing out because we are settling all the dirty stuff out, then you have a chance of building with microorganisms, and we get these so-called limestone facies. Now the limestone facies, the shale facies, and the sandstone facies all happen at the same time. There is no time equivalent. They're parallel to each other, right? We're not stacking them on top of each other, at least not yet. So that is somewhat what we call about a sedimentary facies. Right, depending where you are. Close to the coast, it's going to be sand. A little bit further out to sea, it's going to be shale. A little bit further out, it's usually the limestone. And if you go further out than limestone, then comes shale again because the water gets deeper and that's not enough light for building corals at this point. So this is a common sequence that we find in coastal environments. Parallel deposition. Now let's play a little bit of a mind experiment, a simulation if you want. So this is a picture you're seeing right now. This yellow triangle here, ignore it. It's my bedrock. They say fluvial. You can scratch this one out. It's just my bedrock. I have to have some kind of a datum of where to start with, right? And this is a sequence you see again, like you have down here. Of course, you need to flip this whole around. There's my beach. There's my sand. There's my shale. There's my limestone. And that's a little fish. Yeah, just kidding. I don't know what the fish is doing here, but it's basically my ocean. Now let's for a moment assume my sea level is rising. Not all at once, not from here, all of a sudden it's up here, all of a sudden, right? So we gradually rising the sea level. What would happen to the sand? Well, the sand would move with the sea level upward, right? What would happen to the shale? Oh, it would follow the sand upward, right? Over time. Thousands of years, hundreds of thousands of years, millions of years. What happens to my limestone? It would also follow my shale upward, and I would get a picture that looks something like this. So over time, you can see that as my sea level is rising, of course, my beach has to follow suit, and it's going to rise and then move toward the left with it. The shale is following, and now the shale is going to be on top of the sand. Of course, the law of superposition still applies, right? My sand was at first. The shale came later, and eventually my limestone follows on top of that. So we are getting a specific sequence as my sea is what we call transgressing. The technical term for rising in sea levels in ancient times is a transgressing sea. We have a transgressing sea. Now here's something interesting. Usually you don't see that because that may be 1,000 miles from here to there, right? It's a long distance of how far the sea went inland. What we, however, can see as geologists, we can see a little sliver of that, a little stack, a little road cut somewhere where we see sandstone on the bottom. On top of it is shale, and on top of this one is limestone. Something like that, right? Sandstone on the bottom, shale in the middle, limestone on top. This particular sequence, sandstone, shale, limestone, in that order, sandstone, shale, limestone, sandstone, shale, limestone, is called a transgressive sequence. So when a geologist finds that, he knows the sea levels were rising at that time. The sea went inland. It went up. The story of the earth unfolds. How do they know that the sea level was not always static and stayed in one spot? Well, the geologic record is a great storyteller. And so if you find sandstone on the bottom, shale on top of that, and then limestone on top of that, you know that my sea levels were going up. My sea levels were rising. We call this a transgressive or transgressing sea. All right, now we're going to play the opposite. What happens when the sea levels fall again? Now, this is a little bit more difficult to show, but as you can imagine, as we fall again, now my sand has to move on top of this one, and all of a sudden, we should get the reverse order. So let me try to do this one again, right here. So we have been to that point, and now my sea level is going down again, and we're creating the same stack, but in reverse, right? Something like that will happen. We're creating a reverse order. So, with other words, by the way, MFS, called maximum flooding surface, that's the maximum extent of the sea, was right here, and then we're going backwards again at this point. And again, what we will see is not the whole thing, because it may be thousands of miles, like I said, 1,000 or several hundred miles distance from here to there. But we can see a little outcrop of rock right there, and we get to stack something like this. And if a sea is going backwards, we should see exactly the reverse of this stack. Limestone on the bottom, shale on top of this, sandstone on top of this one. This is what we call my regressive sea pattern, or the regressive sea stack. Regression is the sea that when the ocean level falls again, when it moves backward, right? So this is a falling ocean levels. It's regression, or sea regression. Rising ocean levels is transgressive. And we get for a regressive sea that regressive stack, stratigraphic stack of limestone on the bottom, shale in the middle, and sandstone on the top. Storytellers, this is how we decipher the distant past of these transgressive here and regressive sequences as we find them in the rock record. Now, sea levels through the ages. Sea levels were not always static, as I think they went up and down. So what do we know about? How often did this happen? Well, here is a graph that has been created. On the bottom, you see Exxon sea level curve. By the way, these are the time periods, and these are our age in millions of years. Let me just to orient you a little bit. We're going into geologic time. We're still getting there. This is the Cambrian period, so this is the oldest one down there, Ordovician, Silurian, Devonian. This is the Carboniferous period, and this is the Permian. And right there, this little break 250 million years ago about, this is where the dinosaurs start, right here. The dinosaurs go through the Triassic, Jurassic, and Cretaceous. That's where the dinosaurs lived, right through here. And then comes a big dinosaur extinction event about 66 million years ago. And this is the Paleogene and the Neogene sequences. So this is essence today, right? So this is our time period. Time of the dinosaurs goes from here to there. Pre-dinosaur time, ocean critters right down here. And we have sea level changes in meters. Now, this is not just inches or centimeters. We're talking right now about, the sea level rises half of an inch or something like that. No, this is in meters. And there are two graphics shown, and they pretty much tell the same story. The one here was created by an oil company. Now you may be thinking about why does an oil company like ExxonMobil be interested in sea level changes? Well, they know if we have an ocean and we have plankton blooms, we have the possibility of creating a new oil field. So yes, the oil companies are very, very interested in studying sea level rises, because if the water is too deep, they have a problem. If it's too shallow, it's a problem. So they need to just find the right sequence of where they target the oil fields might be. So they do study this, and Exxon has created this sea level change, very, very detailed, from many, many, many of their borehole records. The ones that drill into the ground and they do some measurements and put probes down there and they measure all kinds of things. And so their scientists that work for Exxon have created the sea level change system. And you can see we had actually very low sea levels and very high sea levels here. Right now, where are we sitting? Well, we're sitting in a low spot. Most of the time, our sea levels are much higher. Wow. The problem is, that is one of the problems we see as individuals. We always think about what is now should be the actual thing that should be what it always should be, because we're living in the here and now. Our temperatures should be the way they are right now. Our sea levels should be, and if we deviate from that norm as we're experiencing right now, something must be wrong with the planet. Well, you can see on this one, no, the planet actually likes much higher sea levels for most of the time. We're right now in a what we call zero, our arbitrarily collected zero. That is not the norm. Now, here's a second one. You see the Hallam et al. This was a researcher. He used rock records not from boreholes. It's why his is not that detailed. He used it just from rock outcrops around the world, right? Looking at rock outcrops and finding these sequences, right? Sandstone, shale, limestone, or limestone, shale, sandstone. One was transgressive, one was regressive, and he created this diagram. And you can see he got a lot of things pretty well matching whatever Exxon says from what he researched on land. So yes, sea levels have changed multiple times over the history of our planet. I just wanted to show you this a little bit. Okay, now, stratigraphy and real rocks in the story of formations. We take a look here in the geologic stratigraphic section, Fort Collins, Loveland areas. And let's look at the real rocks for my little diagram here, and we'll explain that. All right, let's take a look at the real rocks here. What do the Precambrian rocks look like? Now, if you've ever been out there, this is my biotitanizes, amphibolites. They're kind of grayish looking. Too bad we don't do a field trip in person. We actually would walk up there and kind of put your hands on it. They're grayish looking, and you already know they look a lot like these sedimentary rocks in your rock bags. There are some gneisses, some schists and so forth. And that's what we also find in Colorado, right? So they're extremely resilient. They are cliff and mountain formers here. So big mountains sticking out, the highest mountains usually made out of that type of a material. The next one, little younger, right? The oldest one is on the bottom, so this is really the oldest rocks. A little bit younger is my Fountain and Ingleside formations. That's the next one. So we're going to take a look at the Fountain formation, and of course that makes a very resilient landmark. For us, it's an arkose. It's an arkosic type rock. Changes from sandstone. There's some shale units in there, but most of it is kind of a conglomeratic, very coarse-grained material, even with some felspar fragments in it. And it forms very resilient hog bags, that Fountain formation. We see this one in Boulder. Here's a Boulder Flatirons right there. and this is what you would get from that formation. It also shows almost the same resilience here in my diagram as my Precambrian rock, so it moves kind of to the right, tells me it doesn't erode that easily. Now we're going to go up here. The Santanka Formation is really difficult to find, closer to Red Rocks. Boulder, it's kind of missing. It starts up from Boulder on up northward toward Fort Collins is where we pick this one up. But usually right on top of that, Fountain Formation, with maybe a little bit of a shady layer of the Santanka Formation siltstone, you get the Lion Sandstone. The Lion Sandstone, again, is mined in Lyons. Of course, if you go to Lyons, Colorado, you'll see big hogbacks of it. Again, it's very resilient. It forms hogbacks. That's my Lion Sandstone. Forget about the Santanka Formation. Really don't need to know it. It's missing in most places. Not that important. One big one here is our Morrison and Lichens Formation and the Morrison Formation. The Lichens is brick red. The Morrison is a slope former, but both of them, Lichens and Morrisons, are slope formers. They are soft, non-resilient, and they form slopes and valleys. So if you go out and hike in slopes and valleys, these are the Morrison and Lichens Formation. Morrison, of course, has been very important for us here in Colorado because it is where we find a lot of dinosaur fossils in the Morrison Formation. All right, on top of the Morrison, right there is the Dakota group. These are some sandstones, and this is a picture. It's maybe hard to see a little bit, but this is a hogback. We see right here, this is the Dakota group hogback, and you're looking here southward. You're actually standing on top of what Dinosaur Ridge is, right? This is a road coming off Dinosaur Ridge down here. And then that is the road in the valley. Red Rocks Park would be over on this end. So you can see that ridge sticking out. That is actually part of the Dakota group. Very resilient, and it forms hogbacks. The lichens and the Morrison Formation, the Morrison is right down here. This is the slope. And then the Lichens Formation would be this big valley down here. So these are very, very soft, right? They would form the valleys. And here you can see the Dakota group, very resilient. Some of you have been to that Dinosaur Ridge Park. You've gone maybe hiking around there a little bit, and you know the dinosaur footprints are actually in the top, in the Dakota group right here. This is the top of the Jurassic. This is where you find our dinosaur footprints. All right, and if you go further up, again, Benton Shale. Shale alone, soft, non-resilient, forms slopes and valleys again. That's what you would get. The Niobrara group is actually a limestone. It's some shale and it's a limestone unit, and it actually forms some blocky cliffs there. So if you find this Niobrara formation, it's somewhat resilient. It forms smaller hogbacks, but because it's limestone, your acid bottle will tell you put a drop on that blocky stuff and it fizzes like crazy. Then you're standing on the Niobrara group, little hogback again. And of course, if you go then to the Pierre Shale, which is very, very thick, what would you get? Well, another valley former, soft. And the Pierre Shale is usually what you see if you stand on the hogbacks at Dinosaur Ridge and you look toward Denver. So if you're in Denver and the Denver Basin, the vicinity, a lot of these places are sitting directly on the Pierre Shale. Not all of them, because there were some other formations deposited on top of the Pierre Shale, not shown here. For example, you would have the what's called the Arapaho Formation and the Dawson Formation and the Denver Formation, and a lot of these other formations. The Fox Hills Formation is actually on top of the Pierre Shale. A lot of these other formations, especially the Dawson in the Denver Basin, were swamps, and they had coal in it, and we'll get some coal mining out of these systems. But that gives you somewhat of a quick overview over the real rocks as they would pop out here as you hike the mountains back and forth. A little bit more of this one is, of course, when you do the field trips, we have some diagrams in there, something like that you can, in my field trip guide, that you can use to orient yourself and kind of figure out where they are. And the neat part about it, if you go to Red Rocks Park, there are some geologic trails and also the Dinosaur Ridge. You may not have paid much attention to it, but they actually label the formations for you. This is cool, walk around. Oh, now in the Morrison. Oh, now in the Lytle formation of the Dakota group. Oh, now in the South Platte formation of the Dakota group. So they give you these little labels, and you know where you are as you hike around in these places. Okay, and that, in a nutshell, concludes our overview of rock formations. And you should be now equipped, fully equipped. You're supposed to know your rocks, right? Right? Your minerals. And you're supposed to also know a little bit about rocks and rock formations. Now you can enjoy going out for field trips the best.